Welcome to this recording where we will do revision of cross products, and in which also at the end I would like to compare briefly the notation differences between the MSD 210 module and the FSK 116 module. Now, when we talk about cross products, let's start off with an example, and that is the moment of a force. I think most of you were introduced to this in the mechanics course in the end of your first year. Let's say we have a force F, as I've indicated in this diagram on the right hand side. And this force F, of course, it's a vector, and because of that it's indicated with this arrow. This force is applied to a structure at a certain point. And we now wish to calculate the moment of this force about another point, point A. Now, to calculate this moment, we can use a cross product. And to do this, we will then define the position vector from the point A about which we would like to calculate this moment to the point of application of the force F. And we'll call this vector the vector R, this position vector R. Then the moment of the force about the point A is defined by this cross product, namely the cross product of the position vector R as we have just now defined it, with the force vector F. Now, this is a matter of definition, but we can perhaps understand more what it means and also get to a way of calculating this cross product if we manipulate this vector diagram a little bit. Now, it is known that in a mathematical sense, it does not matter if we translate any of these vectors, provided that in this translation we do not change their lengths and we also do not change their orientation. So we can rearrange these two vectors so that they start at the same point, so that the origins of the two vectors falls on a coincident point. Then we can, after we've done this, we can then say that the magnitude of the moment of the force F about point A can be calculated with this equation, namely the magnitude of the position vector R multiplied by the magnitude of the force vector F multiplied by the sine of the angle theta, that is the angle between the two vectors when they are so translated that the origins coincide. Now, this easy way of calculating the magnitude of the cross product has one deficiency, and that is that it does not tell us what is the direction of this cross product. The cross product, of course, is a vector also, just like the constituent vectors, and it will have a direction that is, of course, different to both of the vectors R and F. What we do know, though, is that the direction of the cross product is always normal to both of the vectors in the cross product. In other words, the direction of MA as a vector will form a 90-degree angle with the direction of R, and also a 90-degree angle with the direction of F. So that means that if my vectors R and F lie in the plane of the screen or the plane of the board or the plane of the paper, if I draw on paper, it means that my vector MA must be perpendicular to this plane. So it must be either coming out of the plane or going into the plane. Now, this direction can be determined by applying a right-hand rule. The cross product defines, or is defined, or we can say the direction of the cross product is defined by a right-hand rule. What do I mean with this? Well, if I take my right hand and I'm form my right hand in a half fist, in such a way, I position it in such a way that the first vector in the cross product, in this case the vector R, goes through my hand from the palm of my hand on the inside to the back of my hand on the outside, and I then position my fingers, the four fingers other than the thumb, in a direction so that the fingers span the angle theta between R and F, as it's drawn in this figure, then my thumb will be pointing in the direction of the cross product of R with F. In other words, in this sketch, my thumb is pointing out of the page, or out of the screen, from the screen towards the viewer. So this right-hand rule then says that the moment vector of my force, vector F about point A, as calculated by this cross product, is in the direction from the plane towards the viewer. Now, this is a very nice and, in some sense, a very easy way to calculate the cross product, and I'd like to encourage you to use this in the MSD 210 course whenever you can. There's no problem in using this form of the cross product. In the rest of this recording, however, I would like to focus on a different way of calculating the cross product using the unit vectors. And let me introduce this with a first example. Let's have a force F of 20J, as defined here, and I've indicated here also. 20 units in the Y direction. And this force is applied to a structure at a position of 5 meters in the X direction from the origin of this axis system, the point O. So if I want to calculate the moment of this force about point O, I can calculate the cross product. M sub O is 5I cross 20J in terms of what we've just now discussed on the previous few slides. Now, in calculating this cross product, I can say, well, I know that the magnitude of this cross product will be 5 times 20 times the sine of the angle between I and J, which is 90 degrees. The sine of 90 degrees is 1. So the magnitude of my cross product will simply be 5 times 20, which is 100. And the direction can be determined by the direction of the cross product between the unit vector I and J. Now, the unit vector I and the unit vector J, if I take the cross product, I'll get a resulting cross product which is also a unit vector, and that unit vector will be in the direction K. And we will look at this in a little bit more detail on the next slide. On the right-hand side, I'm showing a right-handed axis system. It's really the same diagram that we've used before in the revision of the dot products. So here's my x-axis. This is the origin, of course, the y-axis and the z-axis. And if I now want to calculate the direction of the cross product of I with J, I'll put my right hand in such a way that the I vector in the x direction, the positive x direction, will go from my palm towards the back of my hand through my half fist. And my fingers will span this 90-degree angle between I and J. And if I hold my right hand half fist in this way, my thumb will be pointing in the Z direction. Therefore, the unit vector, the cross product of the unit vector I with the unit vector J is the same as the unit vector K. In the same way, if I hold my right hand in the half fist in such a way that the unit vector J goes through my hand from the palm side to the back side, and my fingers span the angle of 90 degrees between the J and the K unit vectors, my thumb will be pointing in the X direction, positive X direction, or in the I direction, which then confirms this identity. And you can do the same to confirm the other 4 identities on this page. So these 6 identities in total will be quite often used in dynamics, and you should be able to figure them out quite quickly. These are not included in the formula sheet during the tests and the exams, because we believe that you can figure out these quite quickly. I'd like to just dwell for a moment on the issue of a left-handed and right-handed axis system. I don't want to speak too much about the left-handed axis system because I'm afraid that I may confuse you. But perhaps it's good that you just take note of this. In the dynamics course, we will always work with right-handed axis systems, like the one in this example, in the picture on the right-hand side. These 6 identities all apply to a right-handed axis system. What is a left-handed axis system? Left-handed axis system would be one where the x-axis, as an example, would be the same as in this figure. The y-axis will be the same as in this figure, but the z-axis will be in the opposite direction from the one that we've drawn here. In other words, the z-axis will go in this direction. And for a left-handed axis system, if I take the cross product of I with j, I will end up with a value of negative k. Enough said about the left-handed axis system, other than just perhaps reminding you that whenever you do problems in this course, make sure, if you define an axis system, you'll often be required to define an axis system, always remember to make sure that you define a right-handed axis system. And the way to test that is to check whether these 6 identities are true. Okay, so let's move on to the second example. Let's look at the same force of 20J, the force 20 newtons in the J direction. But let's say the point of application of this force is now different from an example 1. And I'd like to calculate the moment of this force about the point O. So I'll define the position vector from the point O to the point of application. And this is then given by 4I plus 3J meters. Now, the moment then is once again defined by the cross product, and I can write it in this way. Now it's important to understand that the cross product do actually satisfy the distributive law. We know that the cross product does not satisfy the commutative law. The cross product of R cross F is not the same as the cross product F cross R. In other words, I cannot swap these two around. I will not get the same result. It is in fact true that if I swap them around, I get the negative result. But we're not going to go there now. But the distributive law is in fact satisfied by cross products. And so we can apply that. So we can rewrite this expression using the distributive law in this way. And then instead of having a difficult cross product to solve, we have 2 easy cross products to solve. In fact, if we look at the second one, it is really easy to solve because we have the cross product between 2 vectors that are parallel to one another. And the cross product of 2 parallel vectors is just a 0 vector. So it means that this cross product can simply be ignored. It doesn't play any role. The first cross product then can be calculated as 4 times 20 is 80 in magnitude. I cross J gives me K. And so my moment of my applied force F about point O is 80K Newton meters. Let's look at a third example. In this case, I used the same point of application as in the previous example. Therefore, my R vector is the same, but I'm now using a different force vector. One that also has a component in the I and in the J direction, not as an example 2 and 1 merely in the Y direction. So the moment of this force F about the point O is once again defined by the cross product. And now I need to once again apply the distributive law, but I need to apply it twice. So I can say for the first time I apply apply it, I will calculate the cross product between the vector 3i and 10i, which of course will be a 0 vector, so I can ignore it. And then secondly, the cross product of 3i with minus 5j, so that will give me minus 15 times the cross product of I with j, which is of course plus k, which gives me this result, minus 15k. So now that was the first application of the distributive law. The second one would be when I multiply, when I calculate the cross product of 4j with 10i, which will give me 40 times the cross product of j with I, which of course is negative k. So that gives me the minus 40k down here. And then lastly, 4j cross minus 5j, it's once again the cross product of two parallel vectors. So that's a 0 vector. So my final result is simply minus 15 minus 40, which is minus 55k Newton meters. Let's make it a little bit more interesting and perhaps a little bit more complicated. We now define the position vector R as a three-dimensional vector. In other words, my point of application of my force on the structure is in 3 dimensions. I may have chosen an axis system to describe my system in such a way that the point of application is in 3 dimensions, and I need a 3-dimensional vector to describe that point. And the force itself is also a 3-dimensional force vector. We can show this perhaps a bit clearer here. You can see the 3 axes, and once again it's a 3-dimensional sketch on a 2-dimensional plane, but our minds can interpret this. So here's my position vector, 3 units in the x direction, 4 units in the y direction, 2 units in the z direction in meters, and then my force vector also a 3-dimensional vector in some other direction. So the cross product can then be calculated as before. We can now apply the distributive law 3 times. Now, in doing this, every time I have a vector in the a component in the I direction in the vector R crossing with a component in the I direction in vector F, I can just ignore it because that will be a 0 vector. So this means that to calculate the cross product, I have the cross of 3i. I can ignore 2i. The 3i with minus j, that gives me minus 3 times I cross j, which is plus k, which gives me this contribution. And then 3i cross minus 3k, that's minus 9 times I cross k. I cross k is negative j. So negative 9 times negative j gives me the plus 9j, this term here. I'm done with this component. I move on to this one. 4j cross 2i is 8 times j cross I is minus k, gives me the minus 8k contribution down at the bottom here. Then 4j cross minus j is 0. 4j cross minus 3k will give me minus 12 times j cross k, and j cross k is plus I, so that gives me this contribution here. I'm done with the 4j component. I move on to the last component of R, 2k. 2k cross 2i gives me 4 times k cross I, which is in the plus j direction, so that gives me this contribution here. Then secondly, 2k cross minus j gives me minus 2 times k cross j. Now k cross j is in the minus I direction, so I've got minus 2 times minus I gives me plus 2, the contribution down here. And then lastly, 2k cross minus 3k gives me a 0 vector. And so I'm done applying the distributive law. I've written down this result, and I can now simply simplify to give me the final result at the bottom here. Now, I'm sure you will all tell me now there's an easier way of doing this, and indeed you are most welcome to use the alternative determinant method of calculating the cross product of two 3-dimensional vectors. And if you do that, you'll find that you get the same result as before. I'd like to just point out or mention a warning here. If you write something like this in the test and exam, it will be fully valid and fully accepted. But I would like to warn you, what I've often seen in the past is that students try to express the cross product with this determinant, but then they leave out this first row, I, j, and k, as if the reader should just fill it in his mind's eye. That is not acceptable, because what you're writing down then is the determinant of a 2 by 3 matrix. And the determinant of a 2 by 3 matrix is not defined mathematically. So you're writing down nonsense. It cannot be interpreted. And therefore it is not accepted. If you write down something like that in your test or exam, you will certainly be penalized for that. So always remember, if you write out a cross product with a determinant, to fill in the first row, I, j, and k, the unit vectors. If you do that and you work it out correctly, you will get full marks for what you will be doing there. Let's move to the fifth example. Here I'd like to calculate what is called a double cross product. I'd like to calculate the cross product Z of the same position vector R cross R cross F, where F also is the same as in example 4. Now, the part between the brackets, we don't need to recalculate that because we've already calculated that in example 4. And the result that we got was what is given here in red. If you don't believe me, you can go back and compare and see that it is indeed the same as what we have in red in the last slide. So now we can simply, once again, use something like the determinant method or the other method and calculate the double cross product to get this final answer. The important point I'd like to stress here is that this result is not the same as the double cross product of R with R cross F. Because in this double cross product, R cross R is a 0 vector. And then a 0 vector cross F is a 0 vector. So it's important to realize that the moment that I have a double cross product or multiple cross products, it is extremely important that I indicate the sequence in which these cross products needs to be calculated. There is no convention in mathematics that determine the sequence. So if the author does not indicate the sequence with brackets, the reader cannot calculate the answer. The reader doesn't know what the author means if he does not include the brackets. So whenever you've got a double cross product or a multiple cross product, you need to insert the brackets to indicate the sequence in which the cross product needs to be calculated. And we will, in fact, in this course, within the next couple of lectures, we'll actually deal with double cross products. This is the end of the revision of the cross products. I'd like to conclude this recording to just focus a little bit on the notation differences between the MSD 210 module and the FSK 116 module that you've done in your first year. I also realized that some of you did this physics module in the second semester, and then for that the module code was not FSK 116, but I'm not sure even what it was. So I hope that you'll understand this and bear with me. Now in the physics course, you use the symbol capital K to indicate kinetic energy, a scalar quantity. In the dynamics course, we're going to use a capital T. Now, why do we use a different symbol? You need to understand that the symbols that are used in presentations of modules are primarily determined by the handbook that is used in the presentation of the module. And of course, we're using a different handbook in MSD 210 than you did in the FSK 116 module. So you now need to make the switch of symbols. If you're going to use in your calculations the notation that you've used in the physics course, you may very well calculate the calculation correctly, but when we try to read what you've written, we will not be able to understand what you've written, and we will probably penalize you for not doing it correctly. Therefore, it's important that you make the switch to a new notation, and you'll find that you'll have to do this quite often in your academic careers. As you progress towards your final year, every time you switch over to a new module that builds onto a previous one, you will invariably have to also switch notations. So it's important that you also acquire that discipline of switching notation. Now, the kinetic energy is perhaps not that confusing, but the work and potential energy is actually, because in dynamics we use the capital U to indicate work, whereas you use the same symbol, capital U, to indicate potential energy in the physics course, where you used a capital W in physics to indicate work. So take note of this, and then the symbol that we use for potential energy instead of U is the capital V. Then linear momentum. Linear momentum is a vector, and therefore we use a vector symbol for that. We use the capital G with a half arrow overhead to indicate linear momentum, whereas in physics a small p with a bar was used. Then the moment of force, we've already seen this in the examples we've done with the cross product just now, the capital M with a half arrow, because of course force is a vector and the moment of force is also a vector because it's a cross product. You've used the Greek tau in the physics course for torque or torsional moment, and as far as I understand, you didn't consider it as a vector, you merely worked with it as scalar, which of course is not necessarily wrong, but it is of course a limited view of moment. So in this course we will use the capital M. By the way, I should also mention that quite often we just talk of the moment, and when we talk of the moment we actually mean moment of force. It's perhaps a sloppy way of talking, because there's also in dynamics moments of other things than forces. You can have moments of various vectors, and you can also have moments of scalars. So just talking of moment is perhaps not sufficient, but if we warn one another about this in advance, if we don't specify the moment of what, we actually mean the moment of force. Another example of a moment is the moment of momentum. Linear momentum is a vector, so I can calculate the moment of momentum. That is angular momentum, and we'll use the capital H with a half arrow, since this of course is also a vector, as opposed to the capital L with a bar that was used in the physics course. I'd like to thank you for your attendance.